Three charged particles are located at the corners of an equilateral triangle as shown. Q is 3.5 microcoulombs, and L, the length of a side of the triangle, is 0.35 meters. Can we calculate the total electric field at the 7 microcoulomb charge? I'm going to start this off as I start off all of these problems with a drawing. I'm going to remove the 7 microcoulomb charge because a charge can't exert a field at its own location. And I'll just focus on the contributions that these two charges make at that point, which I'll call P. So I'm going to call Q here Q2, and this one can be Q3. That'll help me keep track of them a little bit better. So Q2 is 3.5 times 10 to the minus 6 coulombs. Q3 is negative 4 times 10 to the minus 6 coulombs. And we're going to need to know the physical distances between the points and between the point and the charges. It's 0.35 meters. Okay, now let's analyze the situation and see which direction would the contributions to the field point. See, a field due to this Q2 would point away from Q2. You have to imagine what a positive test charge would do. It would want to get away from that positive charge. So this is going to be called E2, the field contribution from Q2. And similarly here, we need a contribution from our negative charge, but negatives pull positives toward themselves. So this is going to be our E3 contribution. Both of them are at unusual angles, so we're going to want to either break it down into X and Y components, or we may want to write it all out in just one line and solve it that way. I'm going to try to solve it in one line here. So let's do this. E total is going to equal E2 plus E3. Simple as that. I'll replace E with its formula. Do it for both. Okay, that's the setup. That would be the setup for any system where there's two charges exerting a field. Now we want to plug in our K's and our Q's and our R's. That's the easy part. The harder part is dealing with the R hats. So let's just remember what an R hat is. It's a unit vector, meaning it has a length of 1. It's dimensionless. And it points from the charge exerting the field toward the point where we're evaluating the field. So this is going to be R hat 2. And this is R hat 3. Okay, so far so good. Now we'd really like to get an angle for these R hats in standard position though. Standard position angles are measured from the positive X direction. Since this is an equilateral triangle, we'll have a 60-degree angle for R2. And we're going to want a 120-degree angle for R3. That's because this is the positive X direction. All right, so I'll just write those down. that theta 2 is 60, theta 3 is 120, because we're going to need that. We're going to replace r hat with the formula r hat equals cosine theta I hat plus sine theta j hat. Okay, let's do it. All right, all we have to do now is just plug everything in and simplify. Okay. All right, so these are our strengths of the E fields. Okay, so I's can combine with I's and J's can combine with J's. I get 276,000 newtons per coulomb I minus 32,000 J. This is the total electric field at the 7 microcoulomb charge. Next, we're asked to find the net electric force on that charge. So now we are going to involve the positive particle. In order to do this, all we have to do is say that the electric force will equal Q times the electric field as a vector, and we already have the electric field in vector form. So let's just do 7 microcoulombs times our vector All right, whenever we have a scalar here times a vector, we want to distribute to all components. Okay, I get 1.93 newtons minus 0.22 newtons, J. This will be the electric force as a vector. And all it says is that if you have a positive charge and a negative charge here on the x-axis, our field points to the right a lot, 276,000 newtons per coulomb, and it points a little bit down. The resultant of that would look something like this. That's E total. If we throw a positive charge into that spot where there's an electric field, that positive charge is going to feel a force. It feels a force in the same direction as the field because it's positive. If it had been negative, it would have been the opposite. But apparently, the force that it feels is 1.93, comma negative 0.22.